Thank you, Jaideep. My talk would be less confusing than my name, so let's start with that. I'm from the National Chemical Laboratory in Pune, and I'm going to talk to you about putting colloids together to form interesting materials. Right? So this is really more sort of a physics of materials talk, where the materials are interesting. Yeah, hold on. Sorry, I'm unable to clip this. So if you can. Right, thanks. So I'm going to tell you about some work that we've done which really we've tried to understand in the last couple of years, which is on sort of a new way of making bonds between colloids, and really that's going to be the focus of my talk. So we are interested in sort of useful materials that we can sort of play around with, sort of large length scale materials, and in many cases we make these materials by putting colloidal objects together. So in this case, for example, you have sort of colloidal particles that are fused together to make, in this case, an aerogel. Now these kinds of materials are things that you encounter in many applications, especially with all the advances that people are making in making more and more functional particles. Now in many instances you make assemblies of these particles that you want to play around with, and so the functionality could be something like the fact that you have these highly porous materials which give you extremely good thermal insulation. But you could also make them with a whole variety of other materials, for example using colloidal nanoparticles, and in many of these materials, these large macroscopic materials fail at low strain. So you take this material and if you impose a small strain on these materials, you can see that there is an increase in the force, and then it sort of fails because as you retract it just sort of falls apart. And that's something you see with aerogels, and you can sort of intuitively imagine this, because you take these materials which are composed of rigid particles and you sort of you bend them or you push them around a little, they fail or they break, right? And the reason for this is kind of intuitive, is really the fact that these particles are sort of glued together using these links, and these links are what make these particles these assemblies brittle. You take these assemblies and you sort of move them, there's a relative displacement between the particles, and that results in failure of these kinds of assemblies. So that's where we started off saying, if there were a way of assembling these things together to form more mechanically robust materials, then that would be something which would be very interesting. We started this work many years ago when we started putting particles in surfactant mesophases. So this is similar to Dhara's talk from yesterday. So what you have is, in this case, a surfactant that organizes to form a mesophase that has a hexagonal order, and so you have surfactant cylinders that are spaced about 5 to 6 nanometers apart. So they look like these focal conic textures under the optical microscope between cross polarizers, and these are materials which undergo this isotropic hexagonal transition at temperatures about 40 Celsius. The materials are gels, so they are very jelly-like, very high viscous materials, and so you can sort of invert the test tube and they wouldn't flow. Once you put the particles in there and you cool them down, what you end up with is networks of these particles. Just to sort of hark back to some of the concepts that were introduced yesterday, these are again very soft liquid crystals. The elastic constant that Dara spoke about for these materials is on the order of 1 piconewton, and you get sort of these length scales of about 10 nanometers. This work, I'm not going to spend a lot of time about it, is just to say that we started looking at what would happen if you put particles in them, and turns out that if you put particles anything larger than 10 nanometers, they would essentially phase separate and sort of decorate the edges of these domains, and you could use this as a way of making networks of these colloidal particles. You can sort of use some simple chemistry to freeze them in place, and you could make colloidal networks, and these are really independent of the chemistry of these materials, right? So you could make them with iron oxide, silica. You could take 2 different kinds of polystyrene and do it sequentially to make interpenetrating networks. You could make them with hydroxyapatite, and then functionalize them with protein. You could do all kinds of interesting things. You could make 3-dimensional protein networks and so on. All of that is fine, but in every single case, yeah. These networks go to the grain, are formed at the grain boundaries, right? but in all these cases, that these three-dimensional scaffolds that we formed, and you can make these centimeters in size, so really large scaffolds that you can play around with. You can manipulate them. They're mechanically robust, but they're still brittle. So if you try and push on them or pull on them, they fall apart right away at very, very low strains, and that's again very intuitive. So this talk is actually going to be a follow-up of some of that work that we've been doing more recently, and it's about a material. I'll sort of play this movie, which when you zoom in, so this is again centimeters in size. So if you look at this material, this is centimeters in size. You can take this material. In this case, it's macroporous, so it's filled with water. You can compress it to about 1/10 of its original size. And what's really interesting is that when you let go of it, it comes back exactly the same way, right? So this material is, like I said, centimeters in size. You can do an SEM of this, and these are porous structures. The pore length scales can be varied. In this case, about this is about 50 microns. And then if you zoom in further, you can see that these walls are composed almost entirely of these particles. In this case, just to make it easy to image, we took 1 micron silica particles, but really you can do this with any kind of particles, and it doesn't have to be silica either, right? And so you have materials which are roughly 90% by weight comprised of silica, and you can see that they recover completely when you compress them up to, and you can do this many times. We made these. I'll tell you how we make them. We make them such that they're macroporous. We have a very large void fraction, about 90%. So I come from a background where we do a lot of work with polymers and filled polymers. So you take a polymer, and for example, it could be a rubber, and you put in particles to it. For example, car tires are made of carbon black particles put in rubber. And there are many instances where you take particles and you put them in soft polymers. Typically, what we know is that if you put in an inorganic or a hard particle into a polymer, beyond about 5% by weight of the filler, you get a material that's essentially brittle. So in this case, what we have is something which is 90% by weight filler with only 10% of the organic, and you still see sort of a remarkable rubbery nature in these materials. And that's really why I think we found these materials very fascinating. Okay, so how do you make these? It's a very simple method. It's sort of trivially simple in a sense. You take these particles. In this case, the example that I showed you, these are silica particles. The particles are about a micron in size. You take a tiny bit of polymer, and it really doesn't matter what the polymer and crosslinker is. In this specific instance, we took an amine-containing polymer, polyethylene amine, with a tiny bit of crosslinker. Again, doesn't matter what the crosslinker is. In this case, it's a diepoxide. The epoxy ring comes next to the amine, opens up, and forms a bond. And then you take this aqueous dispersion and you leave it in the freezer. That's all you do, right? Over time, ice nucleates and grows. It forms these ice crystals. So the yellow is liquid water. It forms the blue crystals, which is ice. The particles get separated to the boundaries of the ice, and you form these kinds of structures, and that's really what you image. You let the cross-linking go. We let it go for a day. It doesn't have to be that long, but we typically leave it for a day. And when you're done with the cross-linking, you can simply thaw the water and it comes out, and you end up with these kinds of structures, right?
So the porosity depends on the concentration?
Depends on the concentration, and you can vary that, right? The pore size also.
The viscosity of the pores might also depend on the rate at which you're freezing your...
Absolutely. That is entirely dependent on how you nucleate and grow the ice crystals. And to some extent, you can control it. It's a lot more difficult to do with ice than with surfactant mesophases and so on. So the idea, so this is a technique called ice templating. It's not something that we came up with. It's been used to make sort of medical materials that were reported 50 years ago. But this idea of cross-linking while it's in the frozen state is something which people hadn't done in the past. It turned out to have these very interesting consequences. One other point I wanted to make is when we first did these experiments, our first thought was, would the cross-linking go at these cold temperatures? This is something we learned in school. You drop temperatures by 10 degrees, and your rate of reaction goes down by a factor of 2. And so when you're doing this essentially in the frozen state, would it go? Turns out there's two competing effects. As you cool it down, the rate of reaction does go down, but at the same time, there is a concentration of these reactants in these walls, and that sort of seems to balance out more or less, and you can get these structures to form at more or less the same time as if you did it at room temperature. Right, so it's a very simple experimental protocol. All you do is you freeze this dispersion, and you form these by cross-linking these networks. So just to remind you, so the inorganic content, you can burn it off and look at how much the organic is. About 90% inorganic. We have a pore volume which is about 90% and a bulk density of about a tenth of that of water. Yeah.
Is it specific for silica or it can be done with acrylates and other materials?
You can do this with any materials. I'll show you examples later. We've done this with completely biocompatible materials. So things like polyclinamine, you wouldn't want to put them in the body, but we've also done this with completely biocompatible materials, and we've implanted them in mice, and they act as good tissue engineering scaffolds. Right. So we went back then to after having made these materials to characterize them. So here's stress strain curves for these materials. So what you see here, let me see if I can move this. What you see here is that the very soft materials. So in the low strain region, there's essentially, so this is a blow up of what happens here. So there's sort of a small linear region, and then essentially there's not much that happens, because what's happening is that the soft walls are sort of compressing. At some point where the walls touch each other, there's a very rapid increase, and you get this increase in the stress. It's reversible. There is some hysteresis. There's some loss that is encountered in this process, but it comes back to essentially the same position when you let it go. So we made these with fluorescent particles. These are polystyrene fluorescent particles. Index matched them and then looked at these, and what you can see is that the pore structure, and I'm not sure how easy it is to see from the back, but as you go all the way from 0 to about 40% at the point at which this takes off, there's really no change in the pore structure. So you're looking down on it as you compress it, and really the pore structure doesn't change very much in that direction. Right? I'll come back to that in just a minute. So I want you to remember that the pore structure doesn't change, in the fact that you have a modulus of about 24 kilopascals. It's very soft. You can cycle this many times. We've done this hundreds of times, and this material is very robust. You can keep cycling it over and over again. It comes back exactly the same way. So what's the origin of this mechanical response? So the first thing we looked at is to worry about whether hydrodynamics of the fluid squeezing out. You remember in the experiment that I showed you, the pores were filled with water. So we varied the rate at which you squeeze this out by over an order of magnitude, and there's no real change in modulus, suggesting that it's not really the pressure to force this liquid out that gives rise to the modulus. Okay. So a slight deviation from the story is to when we characterize the mechanical response of these materials, there's a lot of work known on sort of porous structures and in sort of idealized situations where you can form these strut-like assemblies. And one of the things you notice is that as you decrease the amount of material that goes into the walls, the modulus decreases. And typically for regular open cell forms, you can sort of do a calculation for what these struts will buckle like, and that gives you a decrease in the modulus that goes with the square of the density. So as you go to lower densities, the modulus falls off quite a bit. For random forms, it's even more severe, and this is one of the reasons why it's challenging to get very low very high porosity, very low density materials, is that typically for random forms this G prime falls off very much more rapidly, and I won't go into the details of why that happens. Just to mention that in our systems we observe that the G prime scales actually only with rho star, so it does decrease as you go to lower densities, bulk densities, but not as sharply as you would expect for these forms. Now the mechanism, you can sort of go back and do sort of a first year engineering mechanics kind of a calculation, which shows that this comes from this buckling mode in this material. You can also go back and sort of calculate that this kind of a decrease in the modulus comes from the fact that the walls are actually compressing rather than bending in this situation, and this is for low strains. Okay, so let's come back to this mechanical response. So we have a network structure. I've shown you what happens when you compress it. You get a modulus of about 24 kilopascals. Again, just as a point of reference, if you take a foam like this and it's made only of silica, you would expect to have gigapascal moduli. What we are getting is tens of kilopascals. It's very soft materials, suggesting that the bonding is completely different from what you had if you had a pure silica scaffold. We can take these materials and sort of gently shear them at very low amplitudes of shear, and you get a G prime as you would expect for a network material, which is essentially frequency independent. It has a shear modulus of about 12 kilopascals, which is half of what we saw previously. It was 24 kilopascals. So the shear modulus is about half of the bulk modulus, and that suggests that the Poisson ratio is 0, which means that if you take this material and you squish it down, you essentially doesn't become fatter, right. So you squish it down, typically for a rubber it would become fatter. These materials don't do that, and that's also something you could see with the confocal microscopy. So as you squished it, there isn't really a change in the pore structure that you see in these materials. So such 0 Poisson ratio materials could be interesting because you could squish it down to a small size and then maybe implant it in something and then through a small pore, and then it could expand back to its original position. What we then started looking at was to look at the temperature dependence of this modulus. And what that was something which we found was very unusual. So here's the shear modulus and the Young's modulus, the elastic modulus, as a function of temperature spanning from minus 20 Celsius to plus 120 Celsius, so 140 Celsius range in temperature. And what you see is essentially a linear increase. So E prime is always about 2 times G prime, so the Poisson ratio stays 0. But you see you see essentially something that looks like a linear increase over 140 Celsius in temperature. Now that's very unusual because for most inorganic materials, or if you take you take a bunch of glassy particles and you bond them together, you would expect a decrease in temperature as you go to higher, a decrease in modulus as you go to higher temperatures. What we see is essentially sort of a linear increase in temperature. That suggests that the origin of the elasticity that we are seeing in these materials is probably not enthalpic, and it's probably entropic, like you would see in rubbers and so on. So it's a very unusual response because if you go back and look at sort of the classic textbooks by Gibson and Ashby, what they tell you is that the mechanical properties of these kinds of foams or networks depend on the materials that the cell wall is made from. This is almost all inorganic, and for most metal, ceramics, glassy polymers, you'd expect to see sort of a decrease in the modulus with temperature. What we have is something which shows an increase. And so we believe that it comes really from some kind of exploration of conformational space that's available to these particles in this bonded network. And so the question that we asked is, can you really envision in this sort of elastic network that forms the walls some kind of motion of these particles that gives rise to entropic degrees of freedom in these systems. So what we did is we went to Shankar's lab at TIFR and took these materials and put them down on a glass slide and used a very sensitive technique that he's developed to look at motions of these particles. And what we saw essentially is that so here is one specific fluorescent particle, and the color axis is time going to about 1600 seconds. So it's over a long time scale, and this is sort of a two-dimensional map of the center of mass of this particle. And what you see is you sort of take this particle, it sort of rattles around in this, and then sort of jumps over, rattles around, and essentially sort of seems to not drift away from its original position completely, but it seems to be able to move around over distances that are several hundreds of nanometers. So these are 1 micron particles that we looked at, and these seem to sort of drift over several hundreds of nanometers, suggesting that there's some kind of possibility for these particles to move. Maybe that's one of the origins of the behavior that we're seeing in these materials. But we'll explore this a little more. So the question is, what exactly gives rise to this very strange structure? Because it seems like this motion of these particles gives rise to these conformational degrees of freedom, that gives rise to the fact that you can compress these materials. But what gives rise to this structure of particles bonded in this small organic matrix? So to go back and look at what might be responsible for this, we looked at how do you we tried to create materials using different protocols. So what we have here is experiments to try and understand whether the protocol that we took to make this, where we take the particles, freeze it, and then cross-link the polymers in the frozen state, is to see if that is specifically important. So remember, we started off with particle dispersion in water with a tiny amount of polymer, polyethylene and cross-linker, and we leave it in the freezer. It typically takes about 10 minutes or so to freeze, and then you leave it in the freezer for over a day while the cross-linking happens. The cross-linking takes a much longer time, on the order of several hours. And then you thaw it and you get this elastic material. This is what we've already shown you. What we then did is, after we froze this material, so after about 10 minutes, we pulled this sample out and then we basically sublimed off the ice. So we took it to minus 80 Celsius where there's no reaction that happens, and then you pull a vacuum on it so that the ice comes off, but the structure of that porous structure is retained, and then you put it back into the freezer, and then you allow it to cross-link. Right, so you have two situations, one in which the cross-linking happens while the ice is present that sort of forces these particles together. In another instance, you've taken the ice out, but the structure stays the same, right? It doesn't destroy the structure, and then you go back and you allow it to cross-link, and so you eventually end up with the same structure. So you end up, if you look at SEMs of these, the two materials look similar. We've done, again, we've burnt off the organic, and the organic content is the same. The degree of cross-linking that happens in both these situations is the same. So as far as sort of chemistry or spectroscopic tools that are available to me can tell, these two materials are identical. Right. So again, just to remind you, this is what we got. So you can sort of compress it to about 90%, and it comes back to the original position. These materials, however, do something very different, and this is the work of Karthika, who has a poster on this. And what you see is, unlike the previous materials, as you start compressing this is done without the water in there, but you can start seeing cracks develop, which doesn't show up very nicely in here. Essentially, this stuff just flattens out, right? And so if you look at the stress strain curve for these materials, unlike the previous curves where the stress would come back as you decrease the strain, essentially you have this massive failure. In fact, you start seeing failure at as small as 5%. So this is what you would normally expect. You take particles together, it's a huge amount of inorganic, you put a little bit of strain on it, and it falls apart, right? Somehow what this tells us is that the structure that we are developing with the ice crystals pushing these particles together, and then if the cross-linking happens, you get this sort of unique structure that allows you to relax back to its original position. Right. Yeah. This is a small strain. So eventually, if you go to high enough, so if you go beyond 40%, your Poisson ratio. See, Poisson ratio is a function of the degree of compression, right? So the Poisson ratio is 0 for up to about 40%, where the structure, the cross-sectional area doesn't change. In this case, actually, what you see is you actually see this thing break. So even beyond about 4 or 5% strain, you can actually see cracks develop in this stuff, and it actually falls apart. Right? In the other materials too, if you go beyond 40-50%, then you will see a Poisson ratio that's not 0. Yeah.
In your second case where you remove the water, right?
Yeah.
Is it possible to swell the network and reproduce the whole behavior?
Sorry, say that again.
So, for instance, you are
After I cross-link it.
Yeah.
No. So if I can't reintroduce water into the system, because if I do, then it will fall apart. The particles will want to redisperse. So I can't reintroduce water in the system. I can cross-link it, but by then everything is set. So cross-linking sets the structure in place. Right. So is there something special about? Yeah.
So have you tried doing an amplitude sweep experiment and seeing how they look? I mean, for these different materials. Do you see a peak in your G double prime?
Oh, you mean in the shear? If you're looking at shear modulation. Not really. So these materials are fantastic in compression. They're not so great in elongation. And the reason for that is if you compress a material and it suppresses crack growth. If you start pulling on the material, then the extensile stress will actually will enhance crack growth. And so at relatively modest extensional strains, these things will fall apart. Even sort of the elastic scaffolds will fall apart. Right? So we've done small amplitude shear, but if you do something larger, then there is an extensional component. I think the material will fail beyond a certain point, but we haven't really explored that in detail. Okay, so one of the things that we were worried about is does the fact that water, that an ice crystal will float on water makes a big difference, and so we decided to look at other materials. So in this case, we looked at an organic, fairly polar organic solvent in which we could do the same thing. So instead of taking these particles, polymer and crosslinker in water, we would take them in an organic and then freeze the organic and let this happen, and it does the same thing. So it seems like what's really critical is to make sure that the cross-linking happens in the frozen state, and that's really critical to set up this kind of structure. So what we believe is happening is that if you cross-link something in the frozen state, you set up some kind of unique structure which we don't fully understand as of yet. which doesn't have to do with the number of crosslinks, but maybe has to do with the spatial distribution of crosslinks in this material, that gives rise to some kind of an effective elastic bonding between these colloids. So it's really a way of creating an unusual bond in these systems. We've done things like FESCM, and it's not very clear that there is, we can pick up anything here. One of the things that Karthika has been doing recently, this is in collaboration with Shiva Patil from ICER, is to use sort of an amplitude modulation AFM experiment where you sort of take the AFM tip and you resonate it, and then as you bring it down, it starts. So if you take this AFM and you resonate it, there's some part of the energy that goes into exciting the tip goes into just sort of dissipation to the medium. But then as you come down, there is another part that goes into the dissipation of energy from the sample, right? And so what we've done is we've taken these two scaffolds and we've brought this tip down to try and understand sort of if there's a difference between the links that are created for the plastic scaffolds or the ones that fall apart versus the ones which are highly elastic, and seems that there is about a factor of 3 difference. And so what we are doing here is you're plotting this dissipated energy as a function of amplitude. So here is when you're sort of in air, and therefore there's no sample, there's no dissipation to the sample. And as you come and bring it closer to the sample, you can see that there is an increase in the dissipation. Again, when you touch the sample, it's all sort of just dissipated by the sample. So essentially, this is a plot that goes from 0 and then comes back to 0 at A over A not going to 0. And so this is a measure really of the mechanical dissipation that is experienced by the sample. So we take a couple of points. We take a point which is on the sphere, which is still covered with the organic, and we get some dissipation. This dissipation doesn't really change in the samples which recover elastically if you go to a point between these spheres. But when you do the same thing for the material which is cross-linked in the absence of ice, you see a much larger dissipation. So what this tells us is, I think these are really the first clues that we have, which tells us there's some difference in the sort of spatial chemistry that you see in these materials, which we again, what is the molecular origin of this is something which is not clear to us at this time. Okay, so this kind of materials is not specific to silica. So Samajit was asking me if this, but we can make this from particles which are, which we've made this from a wide variety of particles. I've shown you examples with polystyrene and silica. We can make this with pretty much any particle. It's independent of the particle chemistry. It's independent of the particle size. We see the exact same behavior whether you have 1 micron particle or 25 nanometer particle. We've tried looking at this. Initially, we would do it in an aqueous system. We've tried doing this at different salt concentrations, so it's really not the screening length that matters in this system. We've also do it in air, and it seems to work just fine. We've changed the cross-linking chemistry from a diepoxide to a glutaraldehyde to other kinds of couplings. Doesn't seem to matter. We've changed the polymer molecular weight by orders of magnitude. Doesn't seem to matter. We've also done, having made the scaffold, these are highly hydrophilic because you have these amine groups on there. You can then modify them to make them hydrophobic, and so you can then take these scaffolds and make them essentially hydrophobic scaffolds that you can swell in an organic solvent, and that also seems to display the same kind of behavior. So it really doesn't seem to matter what the chemistry is. Somehow when you cross-link in the frozen state, you create this kind of microstructure that sets the kind of properties that we see in these systems. So one of the things we worried about some time ago is, what can we do with these kinds of scaffolds? And this is what I was telling Samajit, is that we've also made materials which are completely biocompatible. These are made from hydroxyapatite particles coated with gelatin and then cross-linked, and then you can make these scaffolds which can sort of compress into small objects and then sort of implant them in mice and have cells grow in these. One of the things that's nice about these materials, and I haven't spoken about that, is the fact that by changing the cross-link density, you can vary, by changing the amount of cross-linker in there and therefore changing cross-link density, you can vary the modulus of these materials by about 2 orders of magnitude, probably more. We can certainly do 2 orders of magnitude in the lab. What that lets us do is, for example, create materials where the sort of modulus of the material provides cues to the cells and changes the way in which they differentiate inside them. So for example, if you put in stem cells and you put them into scaffolds with different moduli, you can sort of use this mechanical cue to modulate the kind of cells that they will differentiate into. That's something that we are doing. This is work done in collaboration with somebody who knows a lot more about tissue engineering than we do in our group. We can do other things. For example, we can make hydrophobic scaffolds, and these two you can sort of make them such that. So here's not a very good video of oil droplets on water, and you put in this hydrophobic scaffold in there. For some reason, I think my student dyed this stained this with a dye, and it absorbs this. You can take these scaffolds swollen with oil, squeeze the oil out, and reuse it. And so one of the big challenges today in using materials where you want to recover oil from an oil spill is what do you do with it after you're done with it. Typically, you have to burn it or do something like that. In this case, you can actually reuse it by squeezing the oil out of these materials. We've now developed this so you can have sort of a fairly amphiphilic system that you can use for all kinds of lab spills. We have so the materials as we make them will absorb about 30 times their weight in water, maybe about 30 times their weight in chloroform, maybe about 15 times their weight in hexane. But we can actually tailor them so that they will absorb, the same material will absorb 5 times its weight in water or 5 times its weight in organic. Yeah.
So the number of squeezing cycles, does it change? Or
no, except for the first. The first squeezing cycle seems to be different, but everything beyond that up to 500 is the same. The other thing that is kind of fun and exciting for us is the fact that if I decrease the number of particles that I put in here, instead of making sort of a 3-dimensionally cross-linked structure, I can make essentially colloidal strands. And so we can make them by changing the degree of cross-linking. You can either make them highly flexible. So this is actually composed of about 20 particles that form this very flexible polymeric strand. And you can see that over time, this thing will sort of unfold to form the large length scale structure. So essentially, it's a sort of a mimic of a polymer chain. You can make them either semi-flexible or fairly stiff, depending on the way in which you make these kinds of materials. We make these at very low yields, but this is something that we'd like to improve on. This is something which I'm very interested in sort of pursuing and trying to understand what we can do with this. Once you can make these kinds of materials, you can decorate them with all kinds of stuff. You can, for example, put platinum particles on there, run a reaction of that, make active change. You can do all kinds of things with this, and we're trying to mess around with some of these things. Okay, so that's essentially the end of my talk. What I wanted to tell you is about sort of a new method we've developed to create assemblies of these materials. I think the way in which we bond them gives rise to interesting properties. We can make macroscopic 3-dimensional objects, centimeters in size. You can also use the same kind of ideas to make sort of polymeric type strands of these materials, and you see all kinds of interesting things with them. So we are hopefully going to see a lot more interesting things coming out of these materials going ahead. Thank you very much for your attention. I'll be happy to take questions. Yeah.
Have you ever tried to see how sound travels through this medium?
No. So yeah, that's a very interesting question. So we don't know how phonon mode. So these are of course highly disordered, but they're fairly tightly coupled. But that would be a very nice idea of differentiating between sort of the plastic versus elastic scaffolds.
There are a lot of acoustic materials which do very much like this.
That's an interesting idea. I actually don't know where I would. Do you have a way of helping us with that?
Sure.
All right, wonderful. We should talk about this. Yeah, Ganesh.
So you spoke about templating with an organic solvent, DMSO froze. So water is peculiar in that ice expands. What about DMS, the other case?
It doesn't. It doesn't. Yeah, it doesn't. So that doesn't seem to matter. So that's what we want to find out is the sort of the anomalous expansion of ice. Ice as it goes from water. Does that make a difference? That doesn't seem to be it. Sorry, I really don't know. I'd love to know what that is. So we've just started finding out that there are differences that we can actually pick up using these AFM techniques. Maybe sound propagation would give us something interesting, but I really don't know what the molecular origin of this difference is.
Basically, the temperature of the core is what matters, right?
No, because we could.
At a lower temperature.
No. It has to be. So so the other case too. When we remove the ice, you put it back in the freezer and it cross links at the exact same temperature. It's not the temperature that matters. Yep. Yes.
But think like using, say, bidisperse or polydisperse particles so that you fill in the voids.
Right.
Difference?
No, so we don't. So the particles that we use for this, in some cases, have been reasonably monodispersed that you'd expect to see the particles crystallize if you just let them sediment. But we also worked with polydispersed particles that would not crystallize. With the organic in there, we don't really see, if you sort of zoom in on the SEMs, we don't really see sort of local crystalline order in these systems. We've never done bidisperse.
More what I'm interested in is if you made it bidisperse enough that the difference in particle size is big enough so that, say, the smaller one would fill in the interstices of the larger one. Just wonder how much you can vary the mechanical properties of these things.
Right. It's something we could do. We haven't done that as yet. We've looked at sort of variation of the overall concentration, but not at the. But I imagine that in the walls, the particle concentration does not vary much. We've not done bidisperse, so that's an interesting idea. So we.
Yeah, because with monodisperse, you're not going to get much above
Right.
70% or
Right.
so, but with polydisperse, you can get it up as high as you want.
Right, right, absolutely. But there's always also the issue that there is all this squishy organic that's floating around. But
Yeah.
certainly, I'd increase the concentration of our inorganic in the walls with we have bidisperse. Yeah, we haven't done that yet, but that's something which is interesting. Yeah.
So in the last part, you showed these polymer chains.
Mm-hmm.
So how long can you get these chains?
The flexible ones are a little more challenging. So this method that we have for making them with the ice templating, the way it sort of if you just decrease the number of, if you just decrease the concentration, you can get these chains, but you can't get a large enough concentration of these. I'd really like to be able to go to melts of these chains. For the very flexible ones, you can get them about 15 long. But if you want to increase the amount of cross-linker, then for the semi-flexible or the stiff, you can get them 100 mers easy.
So the particles there are about a micron in size.
They're about a micron in size.
So even with single chains, you could look at like translocation through a pore or something, because you can just visualize the whole thing.
Yeah, so one of the things we try to do just to separate these from all the other goop that we make is to try and put them through pores, but they clog very effectively. So it's been hard for us to find really good sort of micron-sized track edge membranes through which we can put these. But we've had no success in looking at that. But you're right. If I put there's a natural osmotic gradient, it should go through a pore, and I should be able to then start looking at things like probabilities of crossing and so on. But we haven't done that.
Okay, I still don't understand when you understood when you compress it, what makes it more flexible? Is there a change in the area, cross-sectional area of these pores?
There isn't until about 40%. Beyond that, and so what we've seen so far is that when you compress it, these objects, these monomers are bonded together by this sort of flexible linker that allows them to move relative to each other, but they're still bonded. So eventually they will come back, right? So they come back to exactly the same position. So they move enough so that the walls locally become fatter. So the overall sample, the Poisson ratio is 0, but I think that's really because the walls are becoming thicker, and that's the other reason why you have this not so steep dependence of the modulus on the bulk density, right? And then beyond about 40% compression, the walls start touching each other, and that's where the stress takes off, right? But what's crucial is the fact that this tiny amount of organic is somehow distributing in this magical way that allows you to move past each other and come back to exactly the same position.
Maybe you said this and I missed it. Are the particles completely coated?
They probably are. We have, well, so
I mean, if you have the ice in there, all right. Suppose it's the case that the ice partially wets the particles, and so that the difference between using ice and not using it is that you have particles in
I don't think so. So what we have, so the other thing I didn't mention is that a lot of the, most of the, in every single case that we've tried so far, even though we've tried different combinations of particles and polymers, there's always been sort of an opposite charge between the particles and the polymers, right? So there is sort of an electrostatic sort of absorption on these. We use a concentration of particles that's high enough that you get significantly more than a monolayer, about 10 monolayers of these, based on sort of hand waving arguments. So for a 1 micron particle, I'd expect to see about a 10 nanometer coat on that, right? When we compare these two cases where you have frozen them versus you've sublimed it, it's unlikely that, I imagine that the structure would be the same. You're, I guess, above the glass transition, so if the ice were contacting the particle and came off, it's possible for the polymer to move there, but I think that as being unlikely. I think you have sort of a, I don't think it's a uniform coat, but I think that the particles are coated.
This is just a hypothetical question. So if you would, for instance, incorporate active particles in your matrix, right, in this class, what do you think will happen with the morphology of the sponge or of the foam after this squeezing?
So we've done it with semi-flexible polymers, and we see that the diffusivities go up a lot, like a factor of 10 over what we would expect. We've never done it on the scaffolds. So this is really after we spoke with Ranajoy after the last meeting. He suggested, why don't you try and make these semi-flexible chains active, which we were able to do fairly easily. So we've looked at sort of diffusion of these, but we haven't done much more as yet.
Done with all the questions? No other burning questions, or you have more something burning here maybe? Then we end the talk by Guru, very fascinating one as usual, and also the session. I'd like to thank all the speakers for providing a real feast of science as a prelude to the feast probably for us. So thanks to all the speakers, and thanks to all three for staying.
So you have to keep your tummies burning for another 20 minutes because lunch will be ready only at 12:30. And lunch arrangements are just as yesterday, which is, registered participants and unregistered participants there. And the other thing is, a few of you have asked me for a participation certificate. So we'll have something ready tomorrow. All you have to do is give your names. So there's a little writing pad there on the first page. Just write your names, and your certificates will be ready tomorrow. Okay? And we can just hang around here maybe for another 10 minutes.
It's incredible that it depends on this detail yet it's so